Hello everyone, welcome to our channel Mathematics Pathshala. This is a problem of CSIR NET December 2023 Mathematical Sciences. The question ID is 704075. This is a problem of linear algebra part C. So first we read the question. Let A be an n by n real symmetric matrix. Then which of the following statements are necessarily true? First option says that A is diagonalizable. Then if A to the power k equal to I for some positive integer k, then A square equal to I. Then if A to the power k equal to null matrix for some positive integer k, then A square equal to null matrix. And option 4 says that all eigenvalues of A are real. So now we have a standard result that every symmetric matrix is diagonalizable and the eigenvalues of a symmetric matrix are all real. So by this standard result, we have here option 1 and option 4 are the correct option because A is a real symmetric matrix. So A is diagonalizable and all eigenvalues of A are real. So now we consider option 2 and option 3. See, here A is diagonalizable. Okay, so first look at option 3. So we are given that A to the power k equal to 0 for some k positive integer k. So it guarantees us that A is nilpotent matrix. This is the definition. We don't need to say guarantee. Yes, it is the definition of nilpotent matrix. So A is nilpotent matrix, and we also know that all the eigenvalues of a nilpotent matrix are 0. So 0 is the only eigenvalue of nilpotent matrix. So surely the characteristic polynomial of A, we denote it chi ax, it will be x to the power n because A is an n by n matrix. Now consider the minimal polynomial of A. So minimal polynomial must be x to the power something because only 0 is the eigenvalue. So x to the power what? This is the question. X to the power what? See, here A is a symmetric matrix, so it is diagonalizable, and we also know that a matrix A is diagonalizable if and only if the minimal polynomial is the product of distinct linear factors. Okay, let me write. A is diagonalizable if and only if this is a very standard result in linear algebra. A is diagonalizable if and only if the minimal polynomial, okay, we are writing in shortly, minimal polynomial of A denoted by max is the product of distinct linear factors. So if this max equal to x to the power something greater than 1, say k, then it is product of x. So this is not the product of distinct linear factors. All the factors are same. So it must be x to the power 1. So it must be x. If it is x square, then it will be product of two same factors x and x. So it must be the product of distinct linear factors. So this max must be x. And since it is minimal polynomial, it annihilates a. So we have maa, that is 0, that is A equal to null matrix. So in this case, A must be 0 matrix, then surely A square equal to 0. So option 3 is the correct option. Now look at option 2. Given that A to the power k equal to I, given that A to the power k equal to I, and this is easy to find that in this case all the eigenvalues of A are the roots of this polynomial x square minus 1. Very easy to find. If we suppose that lambda is an eigenvalue, then there exists some x not equal to 0 such that ax equal to lambda x. Then in this way a square x equal to a lambda x, that is lambda ax, that is lambda square x. And this way we have a to the power k x equal to lambda to the power k x. Then putting this a to the power k equal to I, we have x equal to lambda to the power k x. So we have lambda to the power k minus 1 x equal to 0, that is lambda to the power k minus 1 equal to 0, as x is a non-null vector. Sorry, we have said here that it is the root of this polynomial, so just by mistake I have said it. Here it will be x to the power k. In this case all the roots of all the eigenvalues of a are the roots of this polynomial x to the power k minus 1. Just we find that if lambda is an eigenvalue, then it is the root of this polynomial. So that means all the eigenvalues of a are the roots of this polynomial x to the power k minus 1. And we also know that the roots of this polynomial, if here k is some say even number, suppose 2, so it is x square minus 1, so 1 and minus 1 will be the roots of this polynomial. Say suppose k equal to 4, that is x to the power 4 minus 1, so in this case it is also 1 and minus 1 will be the two roots of this polynomial, and the other two roots will be complex. And also if k is an odd number, say k equal to 3, then this polynomial is looks like x cube minus 1 like this. So only 1 is the real root of this polynomial, other roots are complex. So it is very clear that this x to the power k minus 1, so only real roots of this polynomial are maybe 1 and minus 1. No other roots, no other real roots uh, are the roots of this polynomial, because other roots will be complex. So now as A is diagonalizable, so we have some P invertible matrix such that P inverse AP is a diagonal matrix, say D, and that matrix will contain the eigenvalues as the diagonal position, and all the positions are 0. Since it is diagonal matrix, so we have some P such that P inverse AP equal to this diagonal matrix. So here this diagonal position contain 1 minus 1 or only 1 or only minus 1. The only possibility is all positions may be 1, all positions may be minus 1, and maybe some 1, maybe some minus 1 together. So let me write in this way: 1 1 some 1, and the remaining are say minus 1 minus 1, say minus 1. So now in this case, this matrix P inverse AP whole square, that is D square. So surely when we multiply this matrix, we will have all positions 1 after multiplication, and other positions are 0. So this is actually our identity matrix. And left hand side, what we get? P inverse AP, P inverse AP. That means we will have P inverse A square P equal to I. Then from here we will have P A square equal to, just multiply left multiply by P, and post multiply by P inverse, we will have P inverse, it is I. So we have A square equal to I. So see here, option 2 is the correct option. If this condition holds, then A square equal to I. So here 1 2 3 4 all are the correct options. This is the solution of this problem.